So let's get this out of the way. All right, so morning, thank you, Kelly. Appreciate it. Good morning, folks at home as well. I got Stephanie there already. Let's see who else I got. I can write down. Hello, Stephanie. Folks, here, our goal today is to talk about PE. Maybe you guys could put down that chair between you. Could you put that down, Ulysses? Thank you, Mary. Thank you, Ulysses. Good. I've got Lisa. I've got Frederica. And on Thursday, I'll have all of you, which is really nice. I've got Yo. Hello. Oh. PE diagrams and rates of reactions. So, let me get rid of some of these other things. When last we met, we talked about kinetic energy, and we said that molecules can have a little or a lot kinetic energy. And I don't know if I gave you this term or not. What's the term for the average kinetic energy of molecules? The average. Remy. No? Ooh, shame on me. This is really a science basic, and I didn't tell you. I forgot all about telling you this. The average kinetic energy of some molecules is known as, starts with a T, temperature. I know you and I think of it as a number, but the higher the number, the more the kinetic energy the molecules have. You know what I mean? That's where we get the idea of temperature. Especially if you use a scale that you might have learned about last year, that starts at 0, but not the Celsius scale. Do you know what scale I'm talking about, Remy? The Kelvin scale. What happens at 0 Kelvin, just as a review? 0 Kelvin, what do you know? Negative. Celsius, yeah. But 0 Kelvin, nothing's moving, agreed. So now you know the molecules at 0 Kelvin have kinetic energy. Zero kinetic energy. They're not, that's what's the definition of kinetic energy. Okay, 0 at 0 Kelvin. Good. I realized last time that, sorry, I've been running over from the blue building, that there's 2 terms I didn't talk to you about yet that I really need to, 2 important chemical terms. We might have had them earlier this year, but I want to review them before we do potential energy diagrams. We started last time, but then afterwards I thought, oh, bad teacher, I didn't even talk to him about this. Let's see if you know these 2 terms. I'm going to do it right here. Review, question mark. Have we had this term earlier in this class? An exothermic reaction. We have. Okay, can you read what we have? Or yeah, go ahead, UCN. Okay, so and did we get to that last hour? Yeah, okay, so releases energy. I want some examples from you. What would be some examples? Lisa says we talked about that too. Thank you, Lisa. Give me some examples of an exothermic reaction. Julia, start us off.
Light?
Nah, not really. Light contains energy, but it's not really undergoing a reaction. It's just either touching us or traveling through space or whatever light happens to be doing. How do you know? Yeah. Burning gasoline. We use that because it definitely gives off energy, helps us to run an automobile. Nick?
Like the thing with like a car battery where they make cars.
Yeah. Can I just say any battery running?
Yeah.
If the battery's running, even in your handy, it's giving off energy. We did kind of a dramatic one last time. Let's see if you remember a really dramatic reaction we talked about that would definitely give off energy. Something dramatic from last time, Nick?
Dynamite and this other element.
Okay, exploding dynamite. That would give off a lot of energy, right? So it's exothermic. Can everybody say that word, please? Exothermic? Think of the energy exiting, like leaving, going out. It's going out from the reaction, okay? Okay. The opposite of that, make sure my folks at home can see as well. Yeah, well, the other one we talked about from Lisa and Stephanie is nitroglycerin. That was the other explosive that would definitely release a lot of energy. That's very exothermic as well when it reacts. Oh, I got Keanu as well. Hi, Keanu. Thanks for saying hi. I got you. Make sure I got everybody else. I do. I do. Good. The other type of reaction is called endothermic. I like to think of this as energy entering the system. Or we could say energy must be put in enter. That's how I remember endothermic. We put in to make a reaction happen. Let's look for some opposites. We have burning gasoline, a battery running, or exploding dynamite. What are some things that require energy? Helen? Boiling water. If I stop the stove, it stops boiling. I have to put in energy to do it. That's a good one. Nick?
Your phone, like turning it on without energy.
The turning it on is here. What about if my phone runs down? That's endothermic, Nick.
And also
Charging. Now what's in your phone that we're actually charging?
the battery.
Yeah. The Akku, right? Akku in German, or we can say chargeable battery. I'll just say battery. So if I'm charging the battery, it's endothermic. If I'm using the battery like over here, it's exothermic. Running.
Yeah. Eating.
Eating. Yes, but eating's really complicated because when we eat, we're usually doing it to use the food as well. It's almost like both in one, Remy. I think I'm going to hold that for a little bit. Yes.
It's like you have like a tool that uses the artistry and then connected to the power. The colors are different, like
No, you'd still be using energy. So as you use it, it would give off energy and heat and sniffing the plant or whatever, you
well,
know.
it's still like putting energy into the but like
It's kind of a complicated thing that using a tool like that. I would say that anything that's given off heat as a byproduct is going to be exothermic.
well charging a battery your phone gets like hot after it's
You're right. Okay, good point, Nick. Um, if all the energy was going into charging, then this would be perfect. But you're right. It's probably not a perfect example, Nick.
And boiling water.
Exactly. In fact, you know what I do with a lot of processes? I lose heat, but it's just the way it is. Here's one that you might have learned about. It's something plants do. Starts with pH. Something plants do. Oh, now we got a lot of it. Jonathan.
photosynthesis.
Yeah. Oh, if the sun stops shining, can they do this? Can they do this at night? Oh, so it's endothermic. It requires energy to be put in to happen. So that's one that's going on right now, isn't it? Right there in that plant, right at this moment. It's endothermic. Yeah? Okay, good. The reason I talk about these two is there's reactions that give off heat, and you'll study a lot of those next year, and some that require heat. And boiling is a good example of that because we do it all the time. We know we have to have heat to accomplish it. And both of these can be put in these sorts of diagrams, which we're going to spend today talking a little bit more about, potential energy diagrams. Look at that. Folks at home had that as well. Requires heat, boiling water, photosynthesis. Exactly. Good, Stephanie. Thanks for participating. Sorry, folks at home, I don't always see your answers. I try to recognize everybody. Appreciate that. Okay, let's do some of these diagrams, okay? I'm going to do a diagram for the first thing somebody said. Who said like burning gasoline? That's like the first one we had. Burning gasoline? Marina. Okay, so let's do a diagram for this. So I'm going to say potential energy is called PE in physics and chemistry. For burning gasoline. Okay, here we go. All right. And on this side, we're going to say that's the amount of potential energy. And this is going to be almost like time. We're going to say stages of reaction. I'll let you know what I mean by stages of reaction as we go on. So, folks at home, potential energies on the y-axis, stages of reaction on the x-axis. Here we go. I'm going to put a little line, and that's going to represent our reactants, the stuff we start with, right? I should have asked you that. Shame on me. Well, my reactants, gasoline. What do I need to actually have to burn gasoline? I need another chemical to burn gasoline. I also need, make what?
Fire.
Oxygen, yeah. So I need oxygen and gasoline. However, if I've got some gasoline, like at the Tankstelle, it's not going to suddenly start burning. What's in the car that gets the reaction started? Do we know that, Remy? A spark. It's called a spark plug, Zündkerze. And I've got to have a spark can you guess what it's doing with the molecules? What do you suppose the spark helps the molecules to do that we got to do first? What do I got to do with the molecules first? Many of them? Break them up. So the spark does this. But what that means is, here's what happens. The spark has to be put in. I got to put in some energy so it goes up like this. Until right there. And right at that spot, the molecule is all broken up. And the spark, you're right, helps to do that. Molecules totally broken up. That's a really temporary stage. They're not up there for long. I don't think some of this is yellow. I can even see. Good. What stuff do I get? If I burn gasoline, I get two products. My reactants are oxygen and gasoline. What comes out? Give me one product, Nick? Yeah, but heat's not like a product. I know I get heat, but what chemicals come out?
Carbon.
Carbon what? Not just carbon, carbon dioxide. There's one. Can you guess the other one? Again, I know you'll have this in more depth in chemistry in 9th grade. Randy, got a guess? Water vapor. So my two things I make are CO2 and water vapor, carbon dioxide, water vapor. And here's the deal. Can you guess where they are compared to what I started with? If I'm going to give off heat, as Mick said, where are they going to be compared to where I began? Well, one or the other. You're going to be way down here. So this would be my carbon dioxide and water. And in chemistry, we say that's my products, don't we? So here's my point. If I do this and the things I make are much lower potential energy, then this whole thing is an exothermic reaction. It gives off heat. Here's the amount of energy it gives off. You ready? From here down to here. In chemistry, this is called the change in heat. And of course, we burn gasoline because there's a really big change in heat. It gives off a lot of energy to drive the car forward. And that, folks, all of that is the change in heat. Yeah, some of these folks knew that at home. Lisa knew that, a spark plug, and CO2 was our product that we talked about with Stephanie and Lisa. Okay, the last thing here is this. We had the term, but we didn't use it in a diagram like this yet. We said we need a spark, right? What's this called? I'm going to put a little star there. What's the energy that I got to put in that we said breaks up all the chemicals? We used it in a little other diagrams. Energy to break up all the chemicals. Look back in your notes. What's the energy called to break up all the chemicals? What does it say in orange? It says from here to here, it's change in heat is in orange. I'll not use that anymore. That is hard to see. Change in heat. And then over here, I have a star in blue, and we haven't put what that is yet. But I'm going to put that over here. What is that type of energy, folks? The blue, the spark provides the energy. Jonathan. Super. So we have that term already. Activation energy. Energy to break all of the up. Break all of the up. Starts with a B. The bonds. The bonds. You'll do a lot of bond talk about this next year, okay? Activation energy. And here it's provided by the spark. Okay, now I know I'm sending a lot of new ideas at you today, but I want you to get the big picture. Here's the big picture of chemistry. Almost all of chemistry is this: break bonds, make new bonds. That's chemistry. And look, we're doing it here too. Break bonds in the gasoline and oxygen, break it apart, and then we go over the hill. Whoa, make new bonds. And if the new bonds are really low energy, I release a lot of heat, and that's the orange. So all of chemistry is about that one phrase. I break bonds, and then I make new bonds. That's the whole science of chemistry. Questions from you here or folks at home about this diagram? I'm going to leave it, but I have to put it on the top board, folks at home, because I need another board for the next example. Okay. Move that up again. Hope folks have that at home. Okay, that was an exothermic reaction. So we're going to do one now for an endothermic reaction. And the reaction we're going to do is one that I think I got from Tully. Am I right, Tully? Did you say boiling water? So we're going to do boiling water. I know it's not like a new, it's not like a new molecule for me, but it's still kind of like a chemical reaction, boiling water. And we're going to do another diagram like this. And I'm going to just call it PE and reaction stages. And this time I'm going to put in my reactants. Well, I only got one reactant. So if I'm starting with boiling water, I'll go back to Tully. If I want to boil water, I got to start with water in what phase? Liquid water. So really, we're talking about my whole reactant is liquid water. How do you suppose this diagram is going to look different than the other one? Let's do it in yellow again. This time I got to keep putting in heat, don't I? Good, I got 3 guesses already. What do you think? I haven't heard from UCN today. UCN, how's it going to look compared to that guy over there?
It's going to go down.
Okay, well, I went down.
I mean, like, it's like going to start off.
Ah, okay, like the bump. No, the bump still got to go up. I still got to put in heat. Tilly, what about the energy of these things? Like when I boil water, Tilly, I go from liquid water to what? what do I get once I boil the water? When I boil the water, what do I get? I get water in what phase? Oh, well, you just gotta say it louder. I can't hear. Gas. With a mask on, I can't always tell what people say. Yeah, I get water in a gas phase, don't I? Where's that gonna be till they compare it to down here? It's gonna be a higher, lower energy. What would you guess if it's a gas? Higher. I'm gonna put that up here. Gaseous water. Why don't you say it that way? It sounds kind of fancy. Well, how can I get from here to there? How can I get from here to there? What do I gotta do? You see it? Add heat. In fact, I gotta add heat until all the waters are pulled apart, and then they can form gas molecules, kind of like that. So this energy I put in, I gotta put in a lot. I've gotta have energy enter my system, right? Endothermic. I gotta put in a lot of energy because my product is much higher energy than what I started with. So that's gonna be my, from here to here, my energy. Whoa, that could have been straighter, couldn't it? It's hard to get good teachers, isn't it? Okay, let's try that. That better? Not really. That's about right. So I got to put in all this energy to break up the liquid water, and again, that's my energy to break up the liquid water. What is that? Compare with the other diagram. It's my UCN activation energy. Thank you. And it's a lot more this time, isn't it? And then I get my gaseous water on the other side. So this whole thing from here to here, I'm going to put the lines and then I'll write it in English. Between the two levels, that's the change in heat. So kind of compare the two diagrams. Folks at home, I'm sorry you can't see both. I'm going to switch up and down so we can look at both. So for something like boiling water, I got to really put in a lot of heat to get the water boiled. For the other one, I don't have to put in much heat at all to break up the gasoline, and I get a lot of heat out. So when heat is released, that's exothermic, and I have a really big down. So I get like a big downhill if it's an exothermic. If it's endo, it's an uphill, isn't it? And you know, if I have the stove on and I'm boiling water, what happens when I turn, Jonathan, when I turn the stove off? Yeah, the stove stops producing energy. And what happens to the water? Does it keep boiling? No, it stops, right? Why? Because now the little molecules can't get over what? This hill. I want you to think of you trying to get over a hill. Look at that hill. That's a big hill, huh? You got to have a lot of energy to get over it. That's the stove I was talking to Jonathan about. Look at the other hill. That's pretty short. A spark will do that in an engine, like Remy said earlier, a spark. That's all it takes. This is a big hill, and I got to keep applying heat with the stove, or else it just stops. You know.
So if you flip the reaction, so you get the gas water, liquid water.
Yeah.
You get a lot of energy.
Exactly. Let's sketch that off on the side. I'm going to put here gas, G for gas, L for liquid. I won't write the whole thing, but that's exactly right. So if I go from gas to liquid, it gives off a lot of heat. In fact, here's a kind of a strange thing. I hope it hasn't happened to any of you, but which is worse, getting burnt by boiling water or steam at the same temperature? Steam, because it's here. And not only does it have to cool down, but it's got to give off a lot of energy just to become liquid. A steam burn is very, very painful. Very painful. And that's why. Yeah, it's exothermic if I'm going from steam to liquid. Just the opposite of this. That's a good observation from Marina. Let's see if I get other comments here. I'm sorry, I forget to read here. Yeah, it needs, Stephanie, a lot of energy. That's right. That's what this needed for sure. Yeah, big amount of energy to boil water. Ute. Turns out the diagram I wrote here for Marino, we actually don't need. Here's the cool thing about these diagrams. A lot of chemical reactions can go backwards. Watch this. What if I'm over on this side and I want to go back down to liquid water? I still got to break up the gaseous water a bit, and then they can join and become liquid. And it's a lot easier, isn't it? Now it's mainly downhill. So what I want you to know that we haven't taught you till now is that some reactions go both directions, forwards and backwards. In fact, a lot of reactions go both ways. A few of them really don't.
Like that one.
Once I burn the gasoline, it's pretty hard to get the gasoline back. That reaction pretty much goes one direction and it's done. But some reactions go both ways. Questions, comments? Now, overall, this unit we've talked about rates of reaction, how fast things go. Well, you can probably tell already. If it's a reaction, usually it's faster. Which sort of reactions would you guess are faster? Exo or endothermic? It's not always true, but it's generally true. Remy? No? Yeah. Why are they faster? Because? Yeah. Exactly. It's just a little bit, and then it gives off a whole lot of energy. And to be honest, this energy coming off can be used by other little bits of gasoline to make those become burnt. So exothermic reactions tend to be faster than endothermic. And if you burnt water, if you boil water on a stove, you know that it can take a long time if I have a big pot of water, right? Okay. Exactly. Okay. I want to do 4 diagrams with you and have you sketch them. And we're not going to put so much on each one. So I'm going to write compare 4 PE diagrams. A, B, C. Can I fit them all? Yeah, they can still see. Okay, so here we go. Make sure my folks so we can see all this. Okay, so these are all going to be PE diagrams, and I'm only going to write it on the first, and that's going to be stages of reaction. So they're all the same, but they're all different shapes, aren't they? I want to ask you some questions about these four. So try and write these four down really exactly as I have them, okay? And then we'll take some guesses. Here it is.
Are there like diagrams where like this it's like
Really good question. Are there any diagrams where I go like that and then over and I come to the same spot? You know, I've taught this for 30 years, and Julius, I've never heard of one that's exactly the same on both sides. It seems like it should exist, but I've never seen one in any textbook. So I'll say, Julius, if it does exist, I bet it's pretty rare. Yeah.
Oh, hello there. Hi.
Oh, hello.
How are you? I got my passport for you.
Okay. Gotcha. Okay, Brooks. All right, so questions? Okay. So I'd like us to try and guess the answers to these four questions. Now, I know this is new to you. Mr. Wise, how am I supposed to know? Just guess. If you're wrong, we'll fix it. Okay? So, if you've written the four diagrams down, try and figure out which one are exothermic, and you write those letters over here. Second, try and put them in order. What do you think would be the fastest reaction, blah, 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 to the slowest? Second, number three, put in order, fastest to slowest again, but this time starting from the other side, from the product side and going backwards. Tricky. Finally, I forgot an H. Which of these has the least stable product? And I'll just have you think about that when you get there. Yes, I know you haven't done that before. Try and make a guess. Okay, I'm going to give folks at home and you folks here a few minutes to do these and take your guesses, and then we'll talk about them together. We had, I think, just enough time. So if you don't know, just guess. So just go and go backwards. So pretend you're there, you can go here, and here, and you can go here, and here. So if you're going backwards, first you can be the fastest one, and then to the slowest.
Oh, okay.
So just look at it and take a guess. Like I said, I know this is new to you. But just kind of guess and we'll see right now how things are going. Okay, so which are exothermic? UCM, what did you think?
B and C.
B and C. Let's look at them. B, I start high and I end low. I give off a lot of heat. That's exothermic. C, look at that. That's really exothermic. I start with a high amount of energy. I give off a lot to make my product. B and C is correct. Put in order fastest to slowest, all right? What do you think's the fastest one? Remy? C. It doesn't take much, does it, to get it the reactants broken up. C is the fastest. What might be the second fastest? Telly? B. It takes that much. That's a fair amount, but it's much. Or it's not much, but it's a little more than that. So B. You want to continue? Telly, what did you do after that? Why is D really the slowest, Telly? Yeah, it's the highest amount of energy.
The highest activation.
You got it. And because it's so high, Telly, it takes a lot of energy to get the reactants broken up. So it's pretty slow. Okay, now the reverse one. Pretend, like I said to Nick, that you're starting at the products each time. Well, what if I'm going backwards? What do you think would be the fastest one going backwards? What do you know?
I think it would be exactly that one. B and
D. Okay, look at the hill from D. Look at that. That's pretty easy. Oh, I could go backwards. That's pretty short. I think Marino's right. D is the fastest. Somebody else, can you go from there? Jonathan. A, second fastest. Pretty good hill, but not as not so bad. Keep going, Jonathan. B, yeah, and then C. Good. C, really slow because now going backwards would take a lot of energy to get over that hill. So chemical reactions can go both ways, forwards and reverse at times. Sorry, that's here. Last one. Which has the most stable product? Can you be guessing? Telling?
Oh, I thought it was
Least. Sorry. Which has the least stable product? C. No, C is actually very stable because it's such a drop. Nick?
A.
There's one less stable than A. One less stable. You see that? B. No, B is pretty stable. Tilly. D. Okay, Tilly, the process of elimination. Okay, but why, Tilly, is it got to be D? Can you talk to me about it? Why does that make sense? If I'm here, Brooks,
probably takes so little energy to reverse the reaction.
yeah, this is the problem with making some chemicals in factories. Some of them, it takes so little energy to break apart and go backwards that we say the product's pretty unstable. What chemists have to do is they've got to take this out as soon as it's made before it can bump together and break up and go backwards, which they often don't want. So D is a pretty unstable product. And let's just mark that down. Yeah? Whew, good job. Questions from you about all of this? Folks at home can't see my answer. I'll write it there. So D for 4. Two or three rather is. Whoa, wait a minute. I put that in the wrong spot. B and C are up here. Sorry, and then that one's up here, isn't it? And this one's up here. Sorry, folks at home. I had things written in some wrong spots. And then the least stable is D. Questions from all of you. That's pretty intense chemistry, but chemists use these diagrams a lot. I mean, like real chemists. This is what they use. So if you don't understand it all, you're going to have it again. But there's an introduction for you today about potential energy diagrams. The other ones we did, kinetic energy, are pretty interesting. These are used by more chemists to explain reactions. Mick.
So all the endothermic ones always have like a hill that they have to go up.
Yep.
Alright.
And it's a bigger hill generally than the exothermic.
Okay.
Thanks, everybody. We'll see you, all of you, and folks at home on Thursday. And we'll be in the other room still on Thursday. Okay, thanks everybody at home for participating. We'll see you live here at school Thursday. Bye-bye.